Hello, my name is Mohsen Heydari and I'm presenting a recent paper on learning of k-qubit quantum operators via Pauli decomposition. This is a joint work with Wojciech Spankovski and is being presented at AISTATS 2021. Learning using quantum computers is one of the emerging applications of near-term quantum computers. In this paper, we focus on the fundamental limits of learning using quantum circuits. More specifically, we consider the learning capability of k-qubit operators inside d-qubit systems where k is less than or equal to d. And there are several challenges compared to classical learning. In quantum, we have the no cloning, we have state collapse and stochastic loss because of quantum measurements. The model we are using is as follows. We consider quantum states with classical labels. Here we have a series of samples with classical labels. So we are looking at classical inference of the quantum states. We assume the states are generated randomly based on an unknown distribution D. For simplicity, we consider binary labels. And we assume that the quantum states have states of d qubits, so the dimension is 2 power d. With this model, the predictors are going to be quantum measurements acting on the quantum state of the system and producing an estimate of the label. The prediction loss here then is going to look like this expression, where the first summation ranges over all values of y over the distribution. We can define a loss function between y and y hat, and y hat, which is the estimate of the measurement, is produced based on the Born's law. Based on this, then the goal is to find the best predictor, best quantum measurement predictor that minimizes the loss. And the problem is to understand the sample complexity of training of these models. So this is a very general learning model. It subsumes special cases such as state discrimination, where we only want to distinguish between two known states, and also classical learning, where here exactly quantum and sample complexity are equivalent. To understand the sample complexity, we need to understand the pack learning model. Here is the classical pack learning framework, where here we have a series of samples generated based on an unknown distribution, and there's a C, which is a concept class, as a set of the classifiers. And the algorithm goal is to find or create a predictor Fn such that its generalized loss is very close to the best in the class with high probability regardless of what D is. And this is the definition of agnostic pack learnability. Here is the quantum version of that. Here now CQ is the quantum concept class, and we have a quantum algorithm, and we would like the algorithm to generate a measurement predictor M. To test this measurement M, we apply it on a test sample, and we compare y and y hat, and then we define the predictor's risk. Based on that, we can define QPAC as follows. We say that class CQ is learnable, QPAC learnable if there exists a quantum algorithm that with high probability finds an almost optimal measurement where the loss is close to the optimal in the class. And we want this to hold for all D and rho, and these are unknown in general. We can see that QPAC subsumes PAC. Therefore, quantum sample complexity in general is larger than classical sample complexity. Now, the focus of this work is on k-qubit operators. So these are operations that act on k out of d input qubits. An example of them are shallow width quantum circuits. The classical counterparts are k-juntas, which are the Boolean functions depending on at most k variable out of d inputs. And these functions have been studied extensively in computational learning. From VC theory, we know that the sample complexity of learning k-juntas scales as order of k log d over k plus some epsilon and delta. Now, the question is that what is the quantum sample complexity of k-qubit operators. So first of all, we know that k-qubit operator subsumes k-huntas, so we immediately get a lower bound on quantum sample complexity. But we know that k-qubit operators are much richer. In fact, there are uncountably many such operators, whereas for classical we have only finitely many k-huntas. On the other hand, quantum samples are fragile because of no cloning, non-commutativity, and measurement indeterminism. All that together, we expect that the quantum sample complexity of k-qubit operators be much larger than k-huntas. And in this paper, we prove the contrary, and we show that there exists an algorithm that QPAC learns k-qubit operators with an error that scales up as this, where here the only difference with this bound is that we are going to have 4 power k. So for a small enough k, the quantum sample complexity is going to be comparable with classical one. Here are our main techniques. We use the Pauli decomposition. The Pauli operators, as usual, are these 4 matrices. We can consider their tensor products as follows. And we have the Pauli decomposition, which states that any bounded operator A on d qubits is uniquely written as this expression, where AS are the Pauli coefficients, they are complex numbers, and are calculated based on this trace quantity. Now with that, we establish our first lemma, which is a connection between the Pauli decomposition and the 0-1 loss. So we need a notation. Let's define rho xy as the average state. So here, if we encode the classical label into a qubit, and then if P0 and P1 are the probability of the label being 0 or 1 respectively, then we can define this average density operator. Based on that, we establish this lemma, which states that given any measurement m consisting of operators m1 and m0, its 0-1 loss decomposes as follows, where gs are Pauli coefficients of m1 minus m0, fs are the Pauli coefficients of this special operator fy, which is defined based on this expression, and here z is the Pauli z. Now, given this lemma, now we get an idea of how to construct a predictor. The idea is that let's fix a k-qubit subsystem. We can denote it by a coordinate j, which consists of k positions, basically positions of the qubit, which are going to act on. Once we fix that, then we can define this operator, which essentially is equivalent to the operator in the previous slide, but with Fourier coefficients only Pauli coefficients only corresponding to this coordinate j. Suppose somehow we find an estimate of this operator by estimating these Fourier coefficients or Pauli coefficients. Then we can create a predictor as follows. First, we consider the spectral decomposition of f hat of y. So here lambda i's are eigenvalues and phi i's are eigenstates. Then we can define pi hat of j as a projection onto the positive image space of this operator. Basically, all the eigenstates with eigenvalue which are greater than 0. With that projection, we can create this measurement, and in this theorem, as one of our main results, we show that if j star is the subset that maximizing this term, then m of j star has a 0-1 loss which is close to the optimal in the class plus some additional term. And here this is a 1 norm of the operator, and here this is a 2 norm of the difference of these two operators. Essentially, this theorem states that in order to minimize this excess error, we just need to find a way to estimate the Pauli coefficients. And here is the process. So the process is that suppose we want to estimate only one Pauli coefficient, let's say one Fs. We can do that by creating this measurement where sigma minus of S is the negative side of the tensor product Pauli, and the other one is the positive side. I mean negative eigenvalues with negative eigenstate with negative eigenvalue, and eigenstate with positive eigenvalue. So if we apply this on each sample and take the empirical average with this normalization factor 1 over 2d and with this expression, then if Zi is the outcome of the measurement on each sample, we get a value f hat, and then we can show that f hat is a good estimate of f, and the excess loss is going to look like this. Now the issue is that we want to estimate several coefficients, but the issue is that the Pauli measurements do not commute with each other, and therefore we cannot simultaneously measure all the Pauli coefficients. Well, the naive strategy states that we can use fresh batch of samples for estimating each coefficient, but the issue with that is there's going to be a factor capital K sitting here because of the union bound, and this is not efficient. We know that this K is very large. So as our second result, we use the idea of shadow sampling, and then we come up with an algorithm that can estimate the Pauli coefficients with an error that scales with log of K. So compared to the previous one, this is a logarithmic improvement. And the idea of quantum shadow sampling is inspired by the well-known shadow tomography of Aronson and the result of Huang et al. And the idea is as follows. So in this paper, we considered quantum shadow sampling on qubits. For that, we show that there's an scalable circuit, which looks like this, that independently works on each of the qubits and produces a shadow. So we take one sample rho I and produce several classical shadows. And the idea is as follows. We generate random unitary operators from this set I, H, S dagger, and H. We apply them on each of the qubits. We measure on the computational basis. We apply the rotations again, and then we apply the inverse of this gamma 0, where gamma 0 is this linear operation. With this expression, we show that the shadow samples are essentially unbiased estimate of the true samples. And based on that, we develop several key lemmas that are listed here. The first lemma states that the optimal loss among the K-Hunter class is decomposed by this one norm expression. The other lemma states that if we have any measurement on the coordinate j with projection pi hat of j, then the 0,1 loss of that measurement decomposes with this. So with these two lemmas together, when we prove that in order to derive bounds on the error, we just need to find a good estimator of the samples, which I presented it in the previous slides. And here is the overview of the algorithm, where we find the Pauli coefficients, estimation of Pauli coefficients using the expression I mentioned. And the sample complexity, we show that it scales with order of k4 power k, and it scales with the logarithm of number of qubits. So this is very good compared to the classical. So we see that they are very comparable as long as k is a constant. We tested the algorithm on a series of numerical experiments. So here the idea is to find a success probability of detecting the maximal entangled states and product states. So on the left hand side, we see the curves for the success probability when we have various number of samples, and on the right hand side we have the size of the system. So here's the conclusion of this talk, and with that I finish.